Good morning, everyone. I'm Carla Barger, co-director of the Digital Humanities Initiative here at UIC. Before we get started, I just want to let everyone know that this event is being recorded. Welcome to our Spring 2021 workshop, Advanced Tools for Digital Humanities, hosted by the Digital Humanities Initiative at the University of Illinois at Chicago. The DHI is designed to expose faculty and students to research in digital humanities and new research methods in the field. The initiative was initially funded by a University of Illinois presidential grant to celebrate the impact of the arts and the humanities, and is a collaboration between the Institute for the Humanities and the University Library here at UIC. We host events throughout the year, including workshops like this one and an annual conference that takes place in the fall. We will have another workshop similar to this one this April, so stay tuned for information on that. So today's event continues the work we began during our fall workshop, Getting Started in Digital Humanities, which I'm sure many of you in the audience attended. Both of today's presentations build on and extend skills acquired by engaging with the somewhat less complex tools and methods that we explored back in September. Machine learning and Python both have wide-ranging applications in various fields. But today we'll learn how they can each be used by digital humanists. In addition, we'll also learn the more advanced applications of Scalar. So, a few logistics. Please enter your questions in the Q&A at the bottom of your screen rather than the chat, and I will read them aloud to our presenters. We ask that you do not screenshot or screen record this event. And when tweeting, please be sure to include the hashtag UICDHI2021. If possible, include the speaker's Twitter handle or full name as a means of citation. And finally, we'll have a 10-minute break, about 10 minutes between each speaker. All right, our first workshop presentation is an introduction to machine learning and its applications in the digital humanities by William Mattingly. William is a postdoctoral fellow for the analysis of historical texts at the Smithsonian Institution Data Science Lab in collaboration with the United States Holocaust Memorial Museum, USHMM, where he is developing machine learning methods to aid in, among other things, a pipeline for automatically processing and cataloging hundreds of millions of Holocaust documents. He is co-investigator and lead developer for the Bitter Aloe project and lead investigator and developer for the Digital Alcuin project. He has a PhD in history from the University of Kentucky, and his dissertation research explored using historical social network analysis, cluster analysis, and computational methods for identifying 9th century intellectual and pedagogical networks. That was a mouthful. And here's William.
Hi, everyone. Thanks for having me. And today I'm going to be talking about Introduction to Machine Learning. So I'm going to share my screen. Hopefully everyone can see it now. And what I'm going to be talking about today is kind of deconstructing the idea of learning, asking some fundamental questions like, can machines learn, and also how they learn. And we're going to do this in the process. I'm going to assume kind of no knowledge on the part of the listener when it comes to either programming or machine learning at all. In other words, I'm expecting the audience to have kind of no background knowledge whatsoever. So kind of building from the ground up. So the first thing I want to really kind of look at is this very basic slide, right? We've got a picture on the left, we've got a word on the right. Just take a few seconds, you don't have to memorize this slide, there's no tricks here. Think about what the image is on the left and think about what the word is on the right. And then throughout this entire talk, I want you to think just in the back of your head, how you kind of arrived at those different conclusions. How did you arrive at what the image on the left was, and how did you arrive what the word on the right was? And what do they mean to you? Just keep those questions in the back of your mind as we go forward. So the first question is, can a computer system learn? And in order to answer that question, which is going to be part 2, we need to start off with one other question first, and that is, what does it mean to learn as a human? In other words, what is learning? And I had this talk done about a year ago, and I've redone it just based on one experience I had over Christmas break. I was at my parents' house, and this isn't a picture of what they have out in their front yard, but they're basically the Griswolds of the neighborhood. They deck everything out, and they have a bunch of those mesh things you buy at Lowe's or Home Depot, and this is a sample of one of the ones that they have. It's obvious to us what this is. All of us on this Zoom meeting can probably look at that, and whatever our mother tongue is what we're going to reference it as in our minds, right? Uh, but the neighbors have a kid, and I'm going to try really hard not to use his or her name right now, trying to keep it as anonymous as possible. And I might slip up. But he comes over to the house, and he's looking at all the decorations, taking them all in, and he pointed at this object, and he said, "Duck." Now, I want to think about what he did there, because this is a common concept in machine learning. And by the end of this talk, you'll understand not only why he did it, but why machines do it, and how we can rethink about how we learn and how we can implement that same concept and process in a machine. Now, this individual called this a duck for maybe one reason. His family has a pet duck that they adopted when they found it injured. It's now a member of the family. This isn't the actual duck, but it hangs out with the dogs in the house. He comes in whenever he wants. He goes to the pond in the neighborhood whenever he wants, but they've kind of taken him in as a family pet. So he is familiar with what ducks are. And yet he looked at this past image and he called that a duck. Now, why did that happen? Well, he doesn't probably have the understanding of aviary genomes, or whatever you want to call it. I'm not a scientist. He doesn't understand the world of biology. He doesn't understand the classification of bird types. Now, he's probably at the age of 1.5 or 2 and 2.5. So he's likely encountered birds in his life, right? He's seen birds in cartoons, in the real world. And so for him, he's probably looking at kind of, without realizing it, without the words of it, he's using what we would call features in machine learning. He's looking at the features of a bird, and he thinks to himself, what makes a bird, this general concept? Well, a bird's got wings, it's got feathers, it flies. Apparently, this is the only image for flies in PowerPoint, a fly. But it has 2 eyes, it's got 2 feet, it's got the characteristic of a bill. And so for him, he knows what birds are, and he knows what ducks are. Now, he doesn't understand the world in any more complex terms when it comes to something that is avian, right? He sees them as ducks and birds. This is hypothetical. Now, if we look at this, we know what separates a duck from a bird. We can look at the images on the left and very clearly say, those are ducks, those are birds. And for him, this is how he understands his whole world. But he also has a couple other things that he understands. He's got pet dogs. So he knows what dogs are. If we think about features when it comes to dogs, they've got some salient characteristics. We all look at these images and we immediately know that's a dog, and this child probably would as well. So what are the features of a dog? Well, dogs, unlike ducks, right, or birds, they've got ears, they run because they've got 4 legs, they have long noses, they've got 2 eyes. These are kind of the features that make a dog, right? These are some of them. There's other ones, obviously. But then he also sees and has experienced in his lifetime cats. Now, let's stop and think for a moment. I found the most adorable photos of cats I could possibly find on the internet. But he's learned about cats, he's seen cats, and he likely understands what they are. And for him, features of a cat, what are they? Well, they've got ears, much like a dog. It runs like a dog. It has 4 legs like a dog, and it's got 2 eyes, and it's got a nose. Now we have a problem. Those features are basically identical to the features of a dog that we just laid out a second ago, right? And so what separates then a dog from a cat from a child's point of view? And I found this lovely image on the internet. This is a image that went viral, I think, a couple of years ago. It's called the internet's cat-like dog, or the most feline dog. And for all of us in this room, we looked at this and we immediately knew, okay, that is a dog, but it's just a dog with very feline characteristics, right? It's got the pointy ears, unlike the dog's droopy ears. It's got the dog's snout, though. It's got the dog's eyes. This is clearly a dog. But we can see, for somebody who hasn't experienced a lot of dogs or a lot of cats, maybe he's only seen 1 or 2 of them in his or her entire lifetime, that might be a challenging question to ask. And this is the concept of learning. So let's go back to that example for one more second. So the young child next door comes over and he sees this thing in the front yard and he calls it a duck. Now, we cannot judge this child for it. First of all, he only lived for a couple of years. He's only had 2 years worth of experiences to really kind of build off of. He's in South Florida, by the way, and probably has never seen a penguin in his entire life. For us, though, we look at this and we know immediately that it's a penguin. Now, is it a fair test for this child who doesn't know the word penguin to assign what we would call a label to that image, to label it a penguin? And the answer is no. And the reason why is because for this child, he is approaching it, doesn't realize it in these terms, he's approaching it as what we would call a multi-class classification problem, which is when you have many different potential labels that you could give to an object. So a label might be a bird, a cat, a duck, etc. So for this child, he's gone through and he's done this first major task. He said, this is not a dog, this is not a cat. What I'm looking at is something that falls in that avian family, right? But what he has done, so he's done the first challenge. It's a binary problem. Is it a bird or is it a mammal? Then the next task then for him is he only knows of birds and he only knows of ducks. Which is it? And he has to make a decision in that moment. Is it a duck or is it a bird? And for him, he made the best decision he could. He said it was a duck. Now, he was wrong. And his parent, great parent, does what any parent would do in that situation, just kind of smiles and says, that's a penguin, and gives them the appropriate label. In the world of machine learning, this is called reinforcement learning, letting a system that is trying to learn make a guess, and when it's wrong, correct it. And that is a foundational principle of machine learning. So hopefully this gives you a sense of kind of thinking about learning. And as we go forward, we're going to think about how to kind of deconstruct that process and how computer scientists and data scientists get this to happen in a computer system. And think about how that child learned from past experiences as we move forward. So big question again. Can a computer system learn? Short answer is yes. Yes, it can. Otherwise, I wouldn't be here talking. To understand why, you have to really understand a single man. Now, I'm a historian, so I enjoy the history of machine learning. This man's name is Donald Michie. Now, Donald Michie was British. He was a contemporary of Alan Turing, the father of modern day computing, and had the famous movie with, is it Benedict Cumberbatch, playing him in Imitation Games. Donald Michie is his contemporary, worked during World War II on a different project, I believe, but he's kind of coming out of that same cohort of individuals. Now, after, I believe he was, let's just say, had imbibed some alcohol at a party and made the audacious statement that he could, in fact, prove that a computer system could learn from past experiences. Now, this is in the 1960s. This was a revolutionary statement. The theory had been kicked around here or there since Ada Lovelace in the 19th century when she develops the first mechanical computer. But really, there was not anyone who actually went out of their way to just say, yeah, I can prove it. And so in the course of one night, he decides to make that his objective. And he invents what would be called the Matchbox Educible Noughts and Crosses Engine, or MINUS. Noughts and crosses is the British way of saying tic-tac-toe, what we would call tic-tac-toe. And I think that's what they call it in Canada too, if I'm not mistaken. And so he calls this MINUS. And if you can't tell from that picture, I'll have a zoomed in photo in just a second. What it is it's not a computer. It's not a computer at all. That is actually a collection of just matchbooks boxes. So the boxes that the matches come in that you would get from Publix down here, I think Kroger up there. So just regular store-bought matches. And he proved that machines could learn with nothing more than matchboxes. So how is this possible? We're going to explore this a little bit more in a little bit. For right now, this is how he proved it. He had each matchbox represent any potential state of the game of tic-tac-toe. And as we're going to see in a later slide, there are 168 different possibilities for the game of tic-tac-toe. Now, this is a computationally easy problem to solve. Can you get a computer to learn how to play tic-tac-toe and play a perfect game? A perfect game is not considered winning. It's considered either a draw or a win. And Donald Michie proved it with nothing more than matchboxes. Well, how did he do it? What he did was he had 168 or so matchboxes, each representing a different state of the game. And if you can see real closely in this image, you'll notice that there's little pieces in there. Those pieces determine which move is going to be made. And so each of those pieces represent a potential move on the part of, let's just call it, the machine, MINUS. As the game progresses, the first game, let's say there are 4 moves in total before the machine loses. At this point, the machine is purely guessing. It's just a person pulling out a random piece to represent a different move in the game. And as the game progresses, those are kept, those pieces are kept. And if that solution led to a loss, that solution is removed. And over time, different poor solutions, if the game is played correctly and no one cheats, the matchboxes that have the better chance of winning are the ones who have beads still in them. In other words, by simply removing failure over random experiences, the matchboxes could prove that matchboxes could play a perfect game of tic-tac-toe. And if done right, then all of the games going afterwards, no matter who is pulling the beads out, it'll always end up in a draw or a win on the part of the machine. No computing power whatsoever. And this was groundbreaking. It kind of paved the way for what would become known as machine learning. Now, machine learning falls under this overarching umbrella category called artificial intelligence. So what is artificial intelligence? It's a word that we've probably all heard constantly. One of the things I want to do today is kind of talk about what AI is, where machine learning fits within it, and more importantly, how machine learning is different from AI, generally speaking. So what is AI? A quick and easy definition that I'll use. There's not really a universal definition of what AI or artificial intelligence is. It's a non-living system that can perform the task that could otherwise be performed by a human. So in other words, it's the migration of human-like tasks or human tasks into a machine. Now, this can be a computer or it can be an example of Minus. Minus is an example of AI, despite not being a computer. So this is what AI is. Now, the biggest problem I have found in teaching AI is that individuals come to the subject with a lot of misconceptions. These misconceptions are perfectly rational. They're grounded in science fiction, they're grounded in movies, they're grounded in pop culture. Um, Things like Terminator, right? Uh, but let's take a step back, try to forget everything you know about artificial intelligence and come to this with a completely fresh mind. There are essentially three different types of AI. The first is artificial narrow intelligence, the second is artificial general intelligence, and the third is artificial super intelligence. I'm going to go through each of these piece by piece. The first one I want to talk about is artificial narrow intelligence. Artificial narrow intelligence is where we're at right now with AI. We're not beyond this. This is where we're sitting at this exact moment. The most advanced computers in three-letter agencies across the country at various universities across the world. This is where the whole world sits with AI. And it means that you get a computer to perform a single task very, very well, and in a lot of cases, either at human levels or beyond human levels. So very specific, narrow, targeted tasks, like playing tic-tac-toe, for example. And I want to talk about this with one example. Here we have probably one of the more famous games of chess ever played. It's Garry Kasparov. Now, this is the start of the game. Don't pay attention to the guy on the right. Not sure who he is. He doesn't really matter for this talk, though I'm sure he's a very important individual. So Garry Kasparov sitting there deep in thought, getting ready to start what would be probably one of the more famous games of his life. He's a grandmaster, one of the greatest chess players to ever live, a contemporary of Bobby Fischer. And I believe, somebody can correct me if I'm wrong, but I believe he was Russian. This is him mid-game. Things are starting to look a little bleak for him. He's really having to think hard here. And then comes the iconic image from this chess match. He loses. Garry Kasparov loses. Now, he's lost plenty of matches in his life, but it's the loss of this match against this man, or possibly the thing behind the man, that causes Garry Kasparov to have so much anxiety. He loses to this, a computer. He loses. This is what the computer. This is actually in a museum now. You can go and visit it. I forget where it's located. It's an IBM museum. But IBM developed Deep Blue, and Deep Blue had a narrow job. Its job was to learn how to play a perfect game of chess. Now, here's the problem, and we're going to see this in a few slides later when we talk about states of games and game complexity. Chess was a very complicated game. Where technology was at the time, this is mid-90s, there was not the ability to teach computer systems. In order for artificial intelligence to really play out and perform a human-like task, it used what we would call a rules-based approach. Now, Deep Blue is very clever. A rules-based approach in computational terms is when you develop a system of rules that a computer system will follow. This will be in a code. The computer system will then, given the state of a game, enact a decision. Now let's take that game of tic-tac-toe again for just a second. Let's go back to it. 168 different state of games that could be played. And this means that I can write a program, but it'd probably take me a couple hours, but I could write a program, and it could consider every single potential state of the game of tic-tac-toe and know the best choice to make. I would just write the rules out for it. So it didn't have to learn. We can write a really good game of tic-tac-toe in probably about 20, 30 lines of Python code, maybe a little bit more. Chess is a little different. There's not 168 different states of the game. As we're going to see, there is 10 to the 120th power states of game called the Shannon number, which we're going to talk about in just a second. So in other words, you can't hard code rules just based on a given state of the game. Instead, those at IBM had to get clever, and they introduced complex rules that would make the best possible decision given a potential state. In other words, it didn't take into account all fun fact, Google is actually the word of the number, all Google number of states. Instead, it would take apart each of those and be able to tackle them individually given an algorithm at play. So it was the algorithm in the background, but it was still a rules-based algorithm. We're going to hold off on that for just a second. The other type of AI is artificial general intelligence. And I looked for a good example of this, and it just so happens that my wife and I just got HBO Max, and it turns out the Jetsons are on there. So I've been binge watching the Jetsons. And it dawned on me that a perfect example of artificial general intelligence is Rosie, the famous robot made from the Jetsons. And I never realized as a kid how funny Rosie was as a character. And so Rosie is a good example of artificial general intelligence. Why? Because she doesn't just perform one task. She can throw the football with the son. Is it Leroy? I can't remember now. She can throw the football with the son. She can clean the house. She can take care of a bunch of different tasks. This is artificial general intelligence. She has the ability to perform multiple tasks at a human level. Artificial general intelligence. We are not there yet. Possibly in the next couple decades we will be, but we're not there yet. The next stage, and this is the one that probably scares people, is artificial superintelligence. This is the one that you probably are thinking of when you come to AI for the first time with no background knowledge in the subject. This is the artificial intelligence that supersedes human-like intelligence. In other words, it can not only perform all the tasks a human can, it can perform more. And not only that, it can perform them exponentially better. And once artificial superintelligence kicks in, there's a lot of rules or schools of thought on this, but chances are it'll be exponential, it'll be rapid, and it'll, in theory, expand faster than we could possibly control it. And eventually you get Skynet and, Armageddon bombs, everything, the whole worst case scenario that could possibly be thought of. So let's go back now to artificial narrow intelligence, because that's where we're going to sit up for the rest of this talk. So we had that game with Garry Kasparov, and like I said, this was an example of a rules-based approach in AI, a rules-based approach. We're not at machine learning yet, but all that's going to change in the late 90s and the early 2000s. There's a rule in computer science that every year computing power, every X amount of years computing power doubles, and this has been proven to be true consistently for the past 30, 40 years. In fact, it's more than doubled in some cases. Late 90s, early 2000s, you have a huge boom in Silicon Valley. And there's different periods of AI that one author has called the AI winters and the AI peaks. This is when AI gets tons of funding from institutions, from governments. And we saw a peak in the 80s, and then it kind of goes away in the 90s. And then all of a sudden in the late 90s, early 2000s, it surges back again. People have this new vigor around AI. And it culminates really in this iconic moment. And this is when AI, in the modern sense, enters kind of the more popular lexicon of people. It's when IBM Watson goes on to Jeopardy, competes, and wins. Now, IBM, same people who made Deep Blue, did something fundamentally different. We're going to talk about that. What they did different was machine learning. But moving forward, I want to talk about one more thing. And that's this photo right here, another iconic image from 2015. This is AlphaGo, which is coming out of Google, playing another game, the most complex game that exists in the world. It's a game that comes out of Asia called Go. And it's playing against the world's expert at the time, not sure he is anymore, Lee Sedol. And this is a famous game in machine learning circles because this is a case where AlphaGo taught a computer for the first time to beat a leading expert, just like Garry Kasparov in the 90s with chess, taught a leading computer to beat a leading expert in a new game. So what makes these things so special? It comes down to one one thing only, and that's game complexity. Now, this is a theory in trying to develop machine learning computers that can play games, because teaching a computer to learn how to win at games is actually a fundamental task for getting it to do other more complex things. So game complexity is about the complexity of a game. In other words, how many states of a game can exist. Whether you realize it or not, when you learn to play tic-tac-toe, what's the first move you always make? You always put the X right in the center, right? And you've learned from past experiences that's a good one to do. But if you're playing with somebody who might be a little smarter than you, you're going to take a risk, and you might go in the top left corner, so you go in the bottom right corner and then catch them by going in the top right corner, and then hopefully forcing them to decide, and eventually you win on the fifth move. But there are only so many states, right, of tic-tac-toe. There's only 168 or so. And this means that tic-tac-toe, with regards to game complexity, is a very simple game. We can teach a computer to play tic-tac-toe very easily. Writing out the rules, as I said, for chess is a much more difficult task. It's called the Shannon number. It's 10 to the 118th or 10 to the 120th, depending on who you talk to. And that number for us humanists who like to see things and not look at powers or factorials or anything like that, factorials, well, this is what it looks like. And fun fact, it's only a few digits removed away from the number that's called Google, which is where Google gets its name, which is 10 to the 100th power. This is what that number looks like. That's how many states that chess can have. That's how many states of game in theory. No one's actually calculated this, as far as I know, or played that many, I should say. This is the amount of states of game. So in order to beat that tic-tac-toe game, if you were taking a rules-based approach, you can do what we call brute force. You can brute force it. You can just throw as many different possibilities at a computer system, and you can figure out the best paths for any different state. That's called brute forcing. It's used in hacking all the time. You hear about brute forcing a server, overwhelming the server so you can actually crack the password based on just billions of guesses. Sometimes rules-based, sometimes just guessing. You can't do that with chess. The computational resources for actually brute forcing that number of state of games is infeasible. It could not be done with computers where they are right now. And that's why I said a few minutes ago that in order to actually solve the problem of beating a human in chess, those at Deep Blue had to get creative. And they came up with algorithms to reduce the complexity and reduce the potential states of games to keep the amount of things that they had to write into the system as minimal as possible. And it took years to do this, over a decade, in fact, to actually be able to achieve this. The difference between chess and Go is a whole other leap in complexity. I don't know the actual number for the states of games of Go. I can look it up at some point if someone's curious, but I promise you it is hundreds of times more complicated in the potential states. I don't know how to play Go myself. Somebody else maybe can contribute in the Q&A if they wish. But let's return back to that image now. Google has to beat Lee Sedol and AlphaGo in the game of Go. And so the team has a challenge on their hands, right? How do you do the problem? You can't brute force this because it's far too large. Writing an algorithm is going to take decades to do, and Google doesn't have time to waste. They don't want to spend 2 decades trying to figure out how to write an algorithm just to beat somebody in Go. So they get creative. So how can they do it? Well, they can rely on the nascent field at the time, machine learning. And this is what AlphaGo was based in. It was based in the concept of machine learning. Now go back to that original discussion in part 1. How do humans learn? We talked about my neighbor's kid, and the neighbor's kid learned really from past experiences, right? His experiences with ducks taught him what a duck looked like. His experiences with other birds taught him what birds looked like. So he could differentiate between mammals and birds in his own mind, not with those words, but in concept. And his experience with cats and dogs meant that he could distinguish between cats and dogs, and plenty of other things, right? Pencil, crayons, he knows what the TV is, etc., couch. These all come from experiences. The child is a living, breathing thing, and in his world, he is looking at things and taking in knowledge. And the parents are saying couch. And over time, he learns the label, the word for couch. Over time, he learns the label and the word for bird or duck or dog, cat, etc. Nonetheless, he learns these things. He learns what's right, what's wrong in theory, probably intentionally breaks some rules so he can learn how far he can push them at the age of what I'm called are terrible twos. I don't have any kids, but that's what I hear. And so these are all part of the learning process for a human. Now, the real question in machine learning is, how do you recreate that process in a computer? We're going to see in a little bit what this looks like. But for right now, let's talk conceptually. So how do you recreate that task of learning? Well, at its basic level, it's the same. You teach a computer through past experiences. Now, the computer has one huge advantage that we as humans don't. For me to become very good at Go, I'm going to probably spend the rest of my life and still be terrible at it. Lee Sedol probably spent a good chunk of his life, and he's amazing at it. He probably has played thousands, if not hundreds of thousands of games in his whole lifetime. I could be exaggerating. I'm not entirely sure. My point is he's played a lot of games of Go in his lifetime, probably one of the most, if not one of the most humans to ever play in the span of human history. Just a guess. Now, the computer has one huge advantage over Lee Sedol, and it's no fault of his. It can process things a lot more quickly. It can learn a lot more quickly if it's given the data or the information in the right format. So what Google decided to do to accomplish this problem, beating somebody in Go, was instead of trying to create rules, they just set up a program that created all the rules of the game Go. So you can only do X moves in certain situations. So just gave it just the rules for the game, the way you or I would learn how to play the game Go. And then it put AlphaGo against another item. And in the first instance, it put it against another human and watched humans play past games. And it looked at those and it found out what moves led to wins in the end. And then what it did was AlphaGo pitted the same computer system against another computer system, both of which had learned from these past games of players. And then it let it just play hundreds of thousands, millions of games over the course of days, weeks, etc. And so in the span of just a very short amount of time, the computer system had played just as many games as Lee Sedol. More importantly, the computer system probably retained information better than Lee Sedol. Now, at the initial stage of this, the computer system was just guessing. It was making guesses. It was saying, okay, I'm going to go here, and I'm going to go here, and I'm going to go here. And it just keeps on guessing. And then initially, it's absolutely terrible. The results are horrible because it's just purely guessing. In the back, though, in the back of the thing is a series of statistical algorithms from linear regression, stochastic gradient descent, etc. We're going to see those in a second. But it's algorithms that are adjusting the parameters based on a loss. And so instead of guessing the next time, it'll guess again, but it's not going to guess the same choice. Instead, it's going to guess something a little different and then see how wrong that move was. And over the course of hundreds of thousands, millions of games, it can hone in those parameters and it can learn what is a great move to make in any given state. Now, it won't have experienced all potential states of the game, but it will have encountered a good deal of them. And then it will be able to do what we call generalize on an unseen state, one that is never encountered before. But it'll know the best move to make because it's looking at the positions of all the pieces. And it knows what the end goal is, which is to win. And it'll make adjustments based on what it sees and make a guess, but a very well-educated guess based on those past experiences. The same way you or I would look at a new animal and make a guess that might be a bird. Now, I have never seen a red-breasted robin in person. Fun fact, the word red actually isn't invented until, or the concept of orange isn't invented until the 1820s. And so that's why we call the red-breasted robin, in fact, red-breasted despite having the orange chest. But I've never seen one in person. But if I looked at a red-breasted robin, I'd be able to say that's a bird. And I can do that. I can generalize on that because I know what birds look like. So how is this? What are the mechanics behind this process that AlphaGo developed? This is what we're going to talk about kind of moving forward now. Deep learning and neural networks. That is really where machine learning sits. Here's a great graph I found a long time ago. I would include the source, but I found it so long ago I forgot to save it. If you Google machine learning, artificial intelligence, deep learning, you can probably find the same image. It's shared across a wide array of online tutorials. But what it does is it perfectly encapsulates the world of AI. AI is this overarching domain within which sits machine learning, and under machine learning is a subfield called deep learning. And deep learning is when we create custom tailored neural networks, which we'll see in just a second, to do a specific task. So behind AlphaGo was a neural network that was making decisions. It was a complex one, but it was making these decisions based on these past experiences and learning. So deep learning is essentially the creation of what we call an artificial neural network. This comes from the same neural network that we have in our brain where synapses are connecting back and forth, but really it's fundamentally different. In distant concept, it functions the same way that our brains do in that it can learn from past experiences, but in practice, it's fundamentally different. And we'll see why when we get to the end of this talk today. So this is a very simple demonstration of what a neural network looks like. The yellow nodes, these are all nodes that you're looking at. The yellow nodes on the left are going to be the input neurons. These are the items in a neural network that receive some kind of input data. So in the case of an AlphaGo match, this might be the state of the game. So, or where all the pieces are. So there would be, the number of nodes would represent all the different pieces on, or all the different board parts, right? So all the different little sections where you could actually move a piece. There would be that many nodes that would be receiving input data. And you can make it more complex than that. Moving on, those input nodes send that data, so whatever they took in, to the next what we call layer. And this is called a hidden layer in a neural network. This is the blue and the green. The yellow is the input layer, and the pink is going to be the output layer. So the green and the blue are hidden layers, and this is where the meat of the neural network sits. This is where all the magic happens. These are nothing more than statistical algorithms that are essentially plotting out data in zeros numerically and making adjustments based on if it was right or wrong. And how does it learn if it's right or wrong? There's a bunch of different ways. There's reinforcement learning, such as the example with AlphaGo, where the machine learned what it did wrong by failing and then making adjustments. The other way it can do this is with something called supervised learning. This is when we give the input data, the yellow nodes, both in the training process, we will give it, let's say we want to teach what the word, let's say we're trying to teach an entity recognizer that can extract entities from a text. We would give it an entire text, and we would have the word, let's say, William is talking right now as the sentence. We would say that the word that begins at position 0 and ends at position 1, William, is in fact a person. And we would give it a whole bunch of sentences like this, 200,000 or so, and eventually it would learn to recognize what names are. And that's how it would learn. And what it does is it goes through and it makes guesses in these blue and green nodes, and it makes guesses as to what it is. And then as it goes through and gets to the end, it sends out an output. And so it might say that the word the, or sorry, talking is a name the first time around. And then it's going to see that the label was wrong. And so what it's going to do, it's going to go back to those blue and green hidden layers and make adjustments. And these are kind of all being plotted out. You don't see this happening unless you want to look at it visually, but it's making these subtle adjustments in a giant scatter plot and kind of adjusting its algorithm to be more accurate. And over the course of, let's just say you have 2,000 training samples that it's going to iterate over, let's say 10 epochs or generations. So 20,000 times, it'll learn what names are so well that in fact, it can be about 98% accurate with a very simple neural network architecture. This is the premise behind a neural network and deep learning. And this, for those who aren't, this is why I didn't show this picture first. It looks scary. This is what's happening in a neural network on a more complex level. What we're seeing here are different algorithms at play. These W's are called weights that are being adjusted. These are the things that guess on what a thing might be. Essentially, it's trying to learn by adjusting. Just imagine a whole bunch. Imagine if you're trying to teach it a vocabulary of 10,000 words. Imagine plotting out each word in 10,000 dimensions. That's what the machine is doing in these hidden layers. And then it's outputting these results, and it'll adjust the weights based on if it was right or wrong. And once it's done training, this model can be saved, and we call it a model, and can be then passed over what we call unseen data, and then be used to do things. So once I've trained a model that can recognize names, now I can just feed it a whole bunch of stuff from Reddit or wherever I want, and I can extract all the names, the people from that text. So that's essentially conceptually how machine learning and deep learning and neural networks work. Now, for the last part of this demonstration, I want to return back to this image that I asked you all to think about before. Hopefully you haven't forgotten about it yet, but let's return to it. So the image on the left and the word on the right. Let's tackle the word first, and I have a little demo prepared for the image on the left. So the word on the right, I'm going to open up the Q&A for just a second real fast, and I can't see it when I'm sharing screen. So Carla, would you mind letting me know what people say? When you look at this word, Paris on the right, what immediately comes to mind? What are the first things that you think of? Oh, I can see the Q&A now. Seine, city, location, France, Eiffel Tower, France, city, Eiffel Tower. Iliad. Oh, That's clever. Okay, I wasn't even thinking that one. Okay, great. Trojan Prince, excellent. Okay, cool. So we've got a lot of stuff here. What we're seeing in this chat is what we call textual ambiguity. The word Paris has a lot of different meanings. I did not think about the Iliad, so I'm really happy I get to spend a little bit more time talking about this now. So great, let's run with that. So we've got people who decided not to take a risk, and I appreciate that because you did the right choice. You said location or city. Now, given the fact that the Iliad is also an option, maybe just a capitalized word would have been a better choice. But let's think for a moment. Let's ignore the Iliad. Let's act like the Iliad doesn't exist for just a second. Let's think of Paris strictly in the sense of a locational sense. So we've got location, city, Eiffel Tower, Seine. I saw a lot of stuff like that. Oh, baguettes. Great. I see baguettes too. So clearly we all have an idea. Now, those of you who said city or location maybe know the trick here. Maybe not. I don't know. But everyone, and I think you wouldn't be wrong for doing this, are immediately thinking of Paris, France, right? Those who said Eiffel Tower, you're committed to this. You thought Paris, France. Those who said city or location, you might still be right. So what if I told you that Paris was in the context of a sentence? These horses look really nice today in Paris. Now, are the horses walking around in Paris, France? Or what if I told you now you're sitting at a cafe in Lexington, Kentucky, having this conversation? Now, are you talking about Paris, Kentucky? Possibly so, which is just adjacent to Lexington, Kentucky, and a really big horse center of the world. Now, what if I told you that same conversation took place right after a trip back from Texas? Now, are you talking about Paris, Texas? My point is this simple word that we think we know with absolute certainty. Paris, it's France, Eiffel Towers, baguette, city, location. We as humans have a hard time understanding what that might be. It could even be a person from the Iliad, from Greek mythology. So to get a computer system to understand text, we actually do a few different things. We can create what are called bag of words. There's other ways that are more complex that I'll get into if somebody wants me to in the Q&A. But this is an example of a bag of words. Every single word in a bag of words has a numerical value. All data, whether textual or image, in order to be processed by a machine for learning, must be converted to numbers. It must become what we call a numerical array, which we're going to see in just a second. So this is what happens here. Paris in this scenario would be given a number. And if we wanted to teach a computer system to do toponym resolution, identifying if Paris is Paris, Kentucky, Paris, France, Paris, Texas, we would give it a whole bunch of sentences in which Paris is used in all of those contexts, and it would learn. It might take about 500 or so samples, but it will learn when Paris is referencing Paris, Kentucky, or Paris, France, or Paris, Texas, and it'll learn from context. It'll look at the words that surround it. It'll learn that whenever it sees Paris, let's say it's number 1, whenever it's alongside baguette, number 2, or Eiffel Tower, number 3, that's definitely Paris, France. Whenever it's around horses, let's say that's number 4, it's always going to be dealing with Kentucky. And when I don't know anything about Texas, whenever it's talking about Texas, that's going to be Paris, Texas. So it learns from context, essentially. Now, I want to hold that thought and move over to, if I can for just a second, can everyone see the thing that is not PowerPoint now? Or is it still showing PowerPoint on your all screen?
No, we can see it.
Oh, perfect. Thank you. So this is just Adam. You're not gonna have to learn code for me. I'm saving all that for Daniela's talk after mine. I'm trying not to step on anyone's toes here. But I'm gonna just simply run a really quick script. And what I am gonna do here is I'm gonna convert right in front of you this picture of an apple, the one we saw a second ago, into what the computer actually sees. So we run the script, it's gonna convert it into what we call a numerical array, a NumPy array. And I don't want to get into it, but NumPy array is essentially a more efficient way of storing data in a computer more efficiently than a typical, what we call a list of numbers. So anyways, what this first line does, I just added this bit of code so it could be more legible. It tells you the width and the height of the image. Let's pull that image back up. Why not? I'll bring this down here. So image on the left, definitely an apple. What am I looking at then? Well, what I'm looking at is, if we scroll all the way down, we'll see 641, and it's, 618 different lines here. And these lines consist of, let me zoom out just a little bit so you can see it all on one page. Zoom out a little bit more. What these numbers represent are pixels. And what each of these lists, we see the open and the close bracket, what each of these NumPy array lists demonstrate is a string of pixels going all the way across. and there are 618 of them going all the way down. So in other words, what it's showing you is a string of pixels all the way across. Now, I can look at this and tell you right now that this is the top of the image, maybe the bottom, but definitely the top. I can promise you that. I know that because I see a whole bunch of zeros, and the 0 tells me what it's looking at is white. That's what 1 means. If we go down, I did this before, and I believe it's lying around pixel set number 26 or so. Here we are. What is that? Those are different numbers, and those numbers correspond to a color. So what am I looking at there? Well, I'm looking at the start, the very start of the contour of the leaf. And if I keep scrolling down, it's getting larger, the leaf is getting bigger and bigger, and then eventually it starts getting larger and larger, and then the leaf will eventually stop. And now I'll start looking at the actual apple. I'm seeing a lot of reds here, a lot of different shades. So we're covering this area right here. And if we keep on going down, the numbers get more and more cumbersome, and we start to actually see an apple taking shape in pure numbers. Now, this might be a little mind-boggling for us, but it really isn't. What the computer is doing here is it's essentially learning what the contours of an apple look like in purely numerical form. And the way you would teach a computer system to recognize an apple, you would give it you would give it hundreds of images of apples, and it would learn the contours from different angles. It would learn the contours that make a leaf. It would learn all these different things that make an apple an apple. And then if you gave it, excuse me, if you gave it a picture of a cat, or if you gave it a picture of another apple, it could tell you that the cat was not an apple, and it could tell you that the apple was in fact an apple, because it had learned what colors make up an apple, what contours make up an apple, because keep in mind, these are pixels reduced to numbers. And if we zoom out, we can see that this really isn't that different from how you or I might learn. In fact, the computer, if we zoom out far enough, is really just looking at the exact same thing that we're looking at. It's looking at an apple as a set of numerical numbers, a numerical array. And even, I think everyone in this Zoom call can look at that and say that's an apple, despite it never having seen an apple look like that whatsoever. And what you're looking at is nothing more than a bunch of numbers between 0 and 255 laid out in a numerical array that represents an apple. And it's only distorted because the numbers are of different size. Were they all separated evenly, you would see this in the exact same proportions as the image to the left. But you can see an apple here. So is it really that infeasible for a computer system to learn what an image is by nothing more than numbers? And the answer is no. So the big question, what do you need to get started with machine learning? While machine learning seems like a daunting thing, it seems super complex, and there's a lot of complexity to it. It's never been easier to learn machine learning than it is right now, because the only thing you really need to learn machine learning is Python. And I'm not going to step on Daniela's toes. She's going to go over Python a whole bunch in just a few minutes. But I'm just going to provide a few resources for getting started with machine learning. I have a website called pythonhumanities.com. It takes you from zero to hero with Python coding. I also have a YouTube channel. If you Google it, it's Python Tutorials for Digital Humanists. And what I do is I walk through not only how to learn Python, but actually how to get started with no background experience with machine learning. I take you through the beginning concepts all the way through for how to do machine learning. So that's my little plug here at the end. But on top of that, Python allows for you to do complex things. And the reason why I said it's never been easier to learn machine learning than it is now, it's because of the libraries that have come out really in the past 5 or so years. Libraries are sets of functions and classes that you can import. So you can do really complex things. I can make a neural network that can recognize, that can differentiate between Oscar Wilde and Dan Brown. I can do that in about 5 lines of code. It'll have to train. It'll take probably about 5 minutes to learn how to do it. My point is that you can do really complex things with very minimal amounts of code. And that's thanks to Python's easy syntax and libraries like scikit-learn, which is kind of rudimentary machine learning, and complex deep neural networks that can be developed with Keras and TensorFlow, which comes out of Google, and PyTorch and FastAI that come out of Facebook. So there's questions, I'd be happy to answer them, but these are some of the preliminary resources for kind of getting started with deep learning. And I'm certain that Danielle is going to have a lot more to talk about with Python. Here, I'll stop sharing my screen now.
That was amazing, William.
Thank you.
I knew nothing about machine learning until just now, and now I feel like I know a lot. Would you mind putting those resources on your last slide in the chat so that everyone in the audience can jot those down when they get a chance? Thanks so much. Let me pull up the questions here. So yes, James Garfield, can we get a copy of this slide? Yes. He's going to put it in the chat
I'll make
right
the
now.
whole slideshow available to everyone if you all want it.
Let's see what else. Thank you, thank you, thank you.
No problem.
Pythonhumanities.com. Okay, so we do have a comment here from Dina Strong. The whole 97% accurate though. There's a reason I, as a human, have to review any auto captioning that's been done, because we get things like introducing our director of library IT, crazy toddler, quote unquote, which is actually Tracy Tolliver. I don't know how they calculate 97%, but my actual lived experience of correcting those captions is that there are errors on at least 50% of the lines. Do you have sort of any response to that, William?
Yeah, it's a result of what we would call general training. And what you're looking at is what we would call a domain-specific problem. So when they trained those captionings, they trained it on a data set that's probably freely available, that's already been labeled. Labeling data takes a very long time, and I can talk about, after I'm done answering this question, why labeling data is kind of a thing of the past already, and why you're going to see that change in the next 2 years, your problem. So you train data, but you train these classifiers. That's what it's, an auto captioner is a classifier, generates kind of text based on what an image is. And it's done that, but it does that by looking at a whole bunch of images, and then the labels that correspond to them are going to be descriptions that were written out by a human. This is usually cultivated data sets on Amazon's web services platform, which is when they pay people like a fraction of a cent to annotate 10 images. This is how a lot of this stuff was collated over the past few years, and the ethicalness of that can be questioned. But that's how this is done. So that's done for a general purpose, so to generalize on most data. Now, what you're looking at is probably something we would call domain-specific data. So data that is relevant to your specific domain, which I gather from the question, I don't see it anymore, but the question dealing probably some aspect of library sciences is what you're looking at, or something along those lines. And you could get a machine to caption things the way that you want them to be captioned by doing what we call transfer learning, or by training one from scratch on your specific domain. So at the Holocaust Museum, and for the Classic Language Toolkit, which I develop NER models for, I develop custom domain-specific NER models to actually solve the problem of general models not generalizing well on domain-specific data. Now, that's going to change in the next few years because of what Google invented in about 2018. It's a new way of teaching systems to learn, especially when it comes to text. And it's called BERT. There's a new one called Ernie, and they have a whole bunch of fun, but it's essentially this the same kind of concept of what they call transformer learning or transfer learning. And so instead of giving let's say you're trying to teach it to recognize text, instead of giving it a whole bunch of text with a whole bunch of annotated data, so entities marked up, this is a name, this is a noun, etc. Instead, what you do is you give it the text with no labels, which is now a lot easier to cultivate. You just go to, Google Books or wherever you can get a whole bunch of text data. It doesn't even matter what it is, and you just give it to it. And then what it does is it takes in, it segments everything by sentence or paragraph, however you want it to be separated. And all it does is remove one word, and it tries to guess what that word is. Now, by guessing what that word is, it's of course going to be horribly, horribly wrong for a very, very long time, and it takes a long time to train these, but you don't have to actually do any work. You just have to, only work you have to do is probably about 7 lines of code, and you can train this really, really complex system that is actually much, much better, sitting at the 98th percentile range, which is considered human-like accuracy, and with very little effort except for the computational expenses of training it. So my point is if that's what you're seeing right now, it's purely because the system you're using was trained on something different, if I had to guess. I'm sorry that was a long-winded answer.
We have several questions in the chat here. William, would you like me to read them out, or did you want to take a look at them? It's up to you.
Yeah, I'll take them one at a time. So it looks like anonymous attendee. I get the name now. Could you give some examples of humanists using machine learning in scholarship? Sure. So that's starting to change. In the past 3 or 4 years, you're really seeing machine learning play a stronger and stronger role in the humanities. So my research is focused on using machine learning to recognize entities and Holocaust documents at the museum where I work. And then I also have taught computer systems to learn Latin, Ancient Greek, Old Norse, Middle High German, Old English, and Ancient Greek now, and classical and medieval Latin, and get them to be able to recognize entities. So identify people in those texts, extract those, identify places in those texts, extract those. And what you have as a result is really rich metadata, data that's found within. Another way that humanists typically use machine learning is with something called text classification. I have an article coming out in the next month or so. I have to revise it in Digital Humanities Quarterly, in which I trained a neural network to recognize medieval variances of scripture and manuscripts. And so you classify texts. So the automation of extracting source material from a text, or the automation of classifying documents. Another way is by topic modeling. So let's say, like, I'm a medievalist, you've got 20 documents, you know that 5 of them are written by one author, 5 by another, but you don't know about the other 10, and you know it's one of the other person. You can do topic modeling and use text classification and machine learning to try and teach a machine to recognize what makes one author distinct from another without having to do 20 years of experience to make those judgments. So there's a lot of different ways, and it's being used right now by humanists to do a lot of handwritten to text transcription. That's just some of the ways. There's a lot more out there. So hopefully I answered that question. I'm trying to go through, because I only have like 8 more minutes. I'm trying to go a little quickly now. So what are examples of applications of machine learning and AI in the humanities, text analysis, image processing? Okay, cool. I think I just did that one as well. Would you comment a bit more about the ethical aspects of using services like, yeah, sure. So this question is about the ethical issues with Mechanical Turk as labels. So I think everyone would agree that paying somebody a fraction of a cent for what amounts to probably about 5 minutes of labor is horribly unethical. The other aspect of machine learning when ethics comes up is, so that's the cultivating of the data. The other aspect of machine learning where you see ethics come out is, and I think it's hinted in the question, is in racism. Racism is inherent. This is known in machine learning as introducing biases into the model. And there was a recent paper that came out that got massively criticized by the entire machine learning community, and even by some humanists who came out as well. And this individual, I can't remember the person's name, it was a terrible paper, argued that they taught a machine to recognize, what was the word they used? It was something very partial. Honesty in paintings from the ancient, medieval, and early modern worlds. The problem is, it was a French author who was using predominantly Western paintings and trying to discern from a single individual's point of view about what honesty looks like, and trying to use pictures from that very narrow data set to identify honesty. Now, naturally, when this was applied to people who were not represented in the data set, the results were wildly inaccurate and ended up being quite racist. This is because the author, who approached it from a very strong bias point of view, introduced the bias into the machine learning model, and the machine learning model then reproduced those biases. In other words, they just basically created a racist AI. That's all they achieved. So that's kind of the ethics that you see pop up in machine learning, both in the cultivation of data sets and the application of it. I know I went through that kind of quickly. So is Python the only language used for the humanities? Are there other ones? No, it's absolutely not the only one. I only encourage Python because it's an all-purpose programming language. There's others out there. The most common one that you see used in conjunction with Python is R. I like using both. I use R for certain things, Python for others. They both have very similar libraries, but what makes Python better, in my opinion, is the fact that you can actually create entire applications with Python. That doesn't exist for R, and R is spelt just like the letter R. And that's used primarily in data science for doing a lot of data cleaning, manipulation, and data visualization. That's typically when I go to R, is for doing data visualization. Thanks so much. Oh, thank you. How
Thank
does the
you.
Oh.
Oh, I'm sorry. Yeah, it's
No
basically 10, William.
Oh.
I'm so sorry.
Yeah, no worries.
If you get a chance, maybe you can respond to some more of the questions while we're having the break, during the break,
Sure.
if that's all right. Yeah, so everyone, we're going to take a small break 5 minutes, I think, since we are running a little bit behind. Thanks to William, whose talk was like too fabulous, right? I'm kidding, William. Thank you so much. It was great. Yeah. When we get back, Introduction to Python and its research applications in the humanities with Daniela Gatti. So let's take 5, everybody. We'll see you back here at 10:05. Okay, we are back. Our next workshop presentation is Introduction to Python and its research applications in the humanities by Daniela Gatti. Daniela is a digital humanist and scholar of contemporary literature, media, and digital culture. Their work examines the relationship between social media forms of anti-racist and queer protest and contemporary dissent fiction. They're also co-authoring a project with an economist that investigates how sentiment analysis of novels can be used to extract information about society's beliefs about its long-term economic prospects. Daniela received their PhD in English from Brandeis University and MAs in English and Economics from the University of Bern, Switzerland. Their dissertation examines the vignette as a counter-hegemonic representational form in and around the book in contemporary print and digital fiction, as well as in a book historical dimension. Take it away, Daniela.
Thanks so much, Carla. I hope everybody can hear me. So I'm gonna start by sharing my screen. And let's see here. Great. Okay, I hope everybody can see this. So basically for this presentation, you're not really going to need any slides, and the materials that Carla has shared with you, I think, in a Google Drive are going to suffice. My recommendation is just follow along with the talk for now, and then you can take away these notes and take them with you home, although you're probably already at home, but you can take them with you and then just replicate what I do here. So following William's fabulous, amazing talk about the conceptual implications of machine learning, we're gonna just do some really, really basic stuff, introducing you to Python. And so really what I want to sort of go over today is what Python is, how to install it very quickly, and then just some basic underlying concepts about how Python works, how to use it, and then we're going to end with a very, very, very short sort of taster of how to use Python for texts. And basically my learning goals here is to sort of grab everybody who may not have used Python or even know anything about Python here in the audience, and get everybody comfortable with the sort of working logic of Python, understanding Python's basic mechanics, and sort of get a bit of a taste for what it might be like to work with texts in Python. And so I think I already told you a little bit about the files. I want to start by talking a little bit about what Python is. William already mentioned it. Python is a programming language. So this means basically that you can, it gives you a vocabulary and a kind of logic for getting different types of computational tasks done. And machine learning is one of those tasks, but you can do other tasks as well. And in digital humanities, typical tasks include things like analyzing large corpora of texts, transforming texts, creating data visualizations, word clouds, and so on. But you can also do mathematical analyses and much, much more. You can build web pages and mailing lists, and you can do all kinds of things. Somebody asked in the chat whether they should be using Python or other languages out there, and R was mentioned as a candidate for that. And yeah, you could basically use anything you want, but Python, in my mind, is it does have a bit of a steep learning curve, especially emotionally. I think for humanists, there's a bit of a barrier, but I think it's also a lot of fun. And for me personally, Python is just kind of the most intuitive of these programming languages that are typically used in the digital humanities. William also talked a little bit about R. To me, the logics of the two are very similar, but Python just makes more sense to me personally. So that's my personal opinion on that. Okay, let's jump into the installation process. So Python is a language. So this means that you're not going to be installing a software exactly to to your computer, because what you want your computer to recognize is that you are writing in that particular language. But you will be installing software that are editors. So for example, Atom that William was using, showing towards the end of his talk. Or, for example, Jupyter Notebook, which is what I'm using currently, which is what you're seeing on your screen. So the easiest way to get something that allows you to work with Python is using the Anaconda distribution, which sort of bundles together software like this, as well as the language itself. And I'm now going to sort of make a little observation here about, which is technically not 100% precise, but just the difference between an editor like Atom, again, from William's talk, and a sort of markdown notebook like the one I'm using here. And the point is that editors or editor shells are used for writing code, whereas notebooks like the one here are used for combining code, which is machine readable, with human readable text. By human readable, I mean that we can read it and understand it easily because we have been trained to do that from early childhood. So something like Jupyter Notebook, which is the current format, is really useful for pedagogical applications or for you to be able to like take notes on your work. So this file, for example, is going to combine the code that's written in it with my notes about the process, which is why I hope it's going to be a good takeaway for you after class. An important point, computationally speaking, what the environment is that you're using to write Python code doesn't matter. As long as the language is recognized, it's really just a personal preference. Yeah, so, okay, so now skipping on to the question of the Anaconda distribution and setting up Python. So once you have these files, you can just follow this link. And this is why I have the files in different formats. So you can, even if you don't have Jupyter Notebook installed on your computer yet, then you can still follow these links. You can go to this website and download the Anaconda distribution for free. I already mentioned that it basically contains the Python language itself, sort of recognizably for your computer. And it also contains a bundle of different programs that you can use to write code. So once you have it installed, you basically get this navigator, which I think is kind of easy for beginners. And you can basically just launch Jupyter Notebook and it will open up in a browser like the one I'm using. So if you're looking at my screen, then you can tell that I'm in Google Chrome. I'm just using a normal browser environment. And that's what happens with Jupyter Notebook. Don't be confused about it because it's still operating on files that are local to your computer, but it's just a browser-based software. So it's going to run in your browser. Okay. My recommendation is basically just take the files that that Carla sent around from this intro and just create a new folder somewhere on your computer locally and put those files there and work there when you return to these things. Okay, I'm going to skip over this little part and jump right into the basic applications of Python. So Python basically Python works by having different types of objects and different ways to manipulate those objects. And the kinds of things you can do with particular objects depend on the object type. So basically what I'm going to go over right now is just different object types and the different ways to manipulate them, which can be functions or methods, as well as some basic operations that aren't so object dependent, which is statements. An important point to understand is that many object types, functions, methods, and so on are inbuilt, but we can also create our own ones, but we're not going to do that today. So some of the main object types that you will typically encounter are, strings, integers, is known as floating numbers, which are basically just numbers, lists, arrays, tuples, dictionaries, and so on. So let's basically jump right in with looking at strings. Strings are basically a sequence of text that Python does not interpret as code. And what I mean by that is that Python won't try to run your string. It's rather a data object that consists of text. So I'm just going to clear any variables that I might have, which is actually like logically or strictly speaking unnecessary, because this is empty as yet. So and let's jump to strings right away. So what I'm going to do in this first line of code is I'm going to create a new variable, which I'm calling my string. And basically I'm assigning to it a sequence of characters denoted by quotation marks that could be, this is a string that I just wrote. Now, if I want Jupyter Notebook to execute this line, I basically press Shift Return, Shift Enter. And now Python has saved this object, this variable, my string, as containing this particular sequence of characters. If I ask Python to print this object now, I'm going to get in the output basically what I told Python that this variable was. So again, Shift Return. And now we've got, this is a string that I just wrote, which is the string, my string. Great. We can also ask Python to tell us what the type of this object, my string, is. And lo and behold, it's a string. So using this function type, I was able to identify the string as a string. But of course, we knew that because I had denoted it initially with these quotation marks. So let's move on to lists. Lists are basically objects that are denoted with square brackets, and they are ordered objects that contain particular elements. So now I'm going to call a new object, my list, and I'm going to define it as a list that consists of the integers 1, 2, 3, and my string. The reason I wanted to do that is because basically I wanted to show you that the type of object that a list contains could be different things. So now if I want to sort of look at my object here, and we're going to print my list, then we're just going to see obviously the same thing again, everything that I input. And notice we see that the string appears here again in quotation marks, except this time single quotation marks. And that doesn't really matter. Python doesn't distinguish between single or double quotation marks. But we've got the list, and we've got the list in its square brackets. So lists are ordered, which means that they have elements that I can access by indexing them, indexing basically their order. So for example, I want to access the first and the fourth elements, and I can do that by telling Python, I want, from my list, I want the element with the index 0. Or from my list, I want the element with the index 3. And lo and behold, indeed, the first and the fourth elements were returned. But why 0 and 3 when I was asking for the first and the fourth elements? And that's because Python starts indexing with 0. And I think William was referring to this as well. This is usual for programming languages. So basically, the first element is indexed with 0, the second with 1, and so on. And this is why I have to access these elements with these numbers. Okay, moving on to dictionaries. Dictionaries are basically objects that, at least in this simple case, associate two objects pairwise with one another. That's where their name comes from, like an actual dictionary. So what I'm going to do here is I'm going to define this new object, my dictionary. I'm going to basically match up the first three numbers in English with the first three numbers in French. Dictionaries are denoted with curly brackets, and the fact that I split it up like this doesn't really make much of a difference. I'm just showing you the sort of pairwise association here rather clearly. But the point is that the dictionary is going to consist of a list of so-called keys, the words in English, which are associated with an element from a list of values. So 1 is with 1, 2 with 2, and 3 with 3, which makes sense because that's their equivalents in these particular languages. So when I run this line, basically I now have a dictionary object, my dictionary, which matches the first three numbers or first three whole numbers with their expressions in French. And notice also that these are strings. So these, they are denoted with quotation marks. So I did not take numbers because that would be difficult to make clear that that would be French or English. Okay, so we're gonna look a little bit more into dictionaries in just a second. But for now, I just wanted you to sort of take away that there are different objects and they have different kind of properties. And in fact, as we now move into the methods section, you'll be able to see that different object types have different methods or different applications that we can put them to. So for example, for a string object, an application that we might want to do is to convert all letters of a string to uppercase letters or capitalize them. So we can use this method, the upper method, and the syntax of methods is always going to be this one. And for this, what I want to do is I'm going to define a new string. I'm going to call it upper string, which basically takes our previous string, my string, and attaches, so to speak, this upper method to it. So when I do that, we see nothing has happened. Well, something has happened, we just don't see it. Is that this new variable has been defined, whereas the old variable, my string, remains unchanged. So let's take a look at it. Instead of using the print function, I'm just going to type the name of the variable. We see that my string has remained unchanged. On the other hand, upper string, which is the new variable that I defined, has really taken the input of the old variable, my string, and just converted it all to uppercase letters. I can also add new text to my string. So for example, I can say that I'm redefining my string as consisting of itself plus some more text that I'm adding to it. So when I run that line and take a look at what this my string looks like now, you see that it has indeed become longer. This is a string that I just wrote and then added some text to. Because dictionaries are different objects than strings, they support different types of methods. And this is really one of the sort of key takeaways about the logic of Python that I would like you guys to take away, which is that we have different kinds of methods associated with the different object types. So remember how I talked about that this dictionary object, my dictionary, consists of keys and values? What if we were interested in seeing like what are the kind of English words, or which English words can I look up in this dictionary object? What is the set of keys that this dictionary object has? Well, there's the keys method for this, where basically I'm just saying, get me the keys from this dictionary object, my dictionary. And lo and behold, now it tells us, it gives us an output where it tells us, indeed, the keys of this dictionary are 1, 2, and 3. Similarly, we can also use the values method to retrieve the values. So meaning basically, what are the French words that are going to, that I have, that is a sort of set of values in my dictionary. So for this, I'm just now defining a new variable, which is going to take as its content the values using the values method from my dictionary. And then I'm going to print that. And notice I'm doing this. There's 2 lines in this line of code, but both of those are going to be executed. And when I do that, we get the answer that we expected, which is 1, 2, and 3. Okay, so we might also be interested in sort of looking up a word in our dictionary. In other words, in using the dictionary to find what the value of a particular key is. So how to say 2 in French, for example. So we can do it in different ways. For example, we can use the get method. So basically here we're applying the get method and we're saying from my dictionary, get me the value of 2, which is 2. Or we could simpler just write, basically I'm interested in the element of 2 with its value. And lo and behold, we've got 2. Great, so let's go into functions a little bit. We've already encountered one type of function, or one specific example of a function, which is the type function, which allows us to identify what type of object we're dealing with. So notice that here I just input a string, de. So it's not going to be a huge surprise that the answer for what type of object it is string. But sometimes we're not fully sure what the types of objects are we're operating with. So it's sort of good to get that information. Then going a bit further down, functions are very similar to methods in Python, and the distinction is not that interesting. But the point that I want to say is that some operations that we perform on objects leave those objects transformed, and others don't. So others just tell us information. So for example, the length function, len, basically just gives us the length, so the number of characters in this case, of, for example, this string, my string. So now I know that the length of my string is 62 characters, but that doesn't change my string. It's still the same string that it was last defined as. Whereas for the list, my list, len tells us that the list consists of 4 elements. But again, the list has not been transformed. Similarly, the print function, which we have been using quite a few times, basically just takes input. And here I'm adding different types of input. So I'm adding my string, I'm adding another random string, and I'm just adding a random number. This doesn't really make sense as an output, but my point is that basically what the print function does is it just returns to me what I gave it and doesn't transform anything. My string is unchanged from this procedure. Okay, sorry for rushing so much, but we have a lot to get to. So now I'm going to look at some basic statements. And if and for statements are very common and intuitive statements, which are going to increase our ability to do things. For example, let's start with the if statement. The if statement is often used to sort of check whether a particular condition is met. So for example, is my string a string? So I could type, if the type of my string is equal to string, remember, this was the answer that Python gave us, so we know that this is Python's language for the type being string. And notice also the equivalence here is different because we're in a conditional statement rather than a definition. So we use 2 equation signs, and the sentence or the statement, the first line of the statement ends with a colon. So if the type of my string is string, then I want Python to print true. It's a string. So let's run that and see what Python tells us. True, it's a string. So Python evaluated that assessment. Is the type of my string string? Yes, it is. And because it is, it's going to perform the activity that I asked it to, which is print true. It's a string. But what would happen if the object that we had in here was not a string? Right now, Python wouldn't really know what to do with that because we haven't specified what to do. So let's do that. And let's use my list as an example because we know that my list is not a string. So the first half of this statement is now going to be the same, except I've added my list. So if the type of my list is a string, then print true, it's a string. Else, print, I guess it's not. And lo and behold, if we run that, I guess it's not. From a literary point of view, it's interesting who the I refers to, but that's a different question. So the point is that basically you can use the if statement here combined with an else to get Python to do more complicated things. Not that this was very complicated, but this is basically the sort of basic functioning of statements. A kind of important note, which I am going to skip over, but if you executed this line here, Python would give you, actually, I'm just going to quickly run it. Python will give you an error message. And the reason for that is because indentation is super important in Python. It basically uses indentation to understand what the sort of logical level of argumentation is. So now it doesn't, now it's looking for, else calls for a beginning. It calls for an if to begin the statement. You can't say like else, Python is like else what? Python, now that it's indented, Python doesn't recognize that this else statement is following upon this if statement. So it's looking for something on this level here that's going to start that statement, but it doesn't find anything. And so it tells us helpfully that there's an error, there's an error with else, and that error is a syntactical one. So anyways, that's an aside and it's an important one. But let's move on and look at a for statement. Suppose we want to do some sort of annoying calculation many times. So for example, in this particular case, suppose that we want to multiply all the numbers in this list with 57. That's annoying. Even just multiplying one of them with 57 is annoying to me. So I'm going to write a for loop to do that for me. So I'm going to say for I, which is an element in this list, 12, 22, and 34, define a new variable x, which is just going to be I times, so it's going to be an element in this list times 57. And then I want Python to print what I is, which is going to be different in every iteration, print a string, and then print the result. So print this variable. So what's going to happen is Python is going to iterate I, which is a previously undefined variable. It's going to iterate I through these different elements of the list. And each time it's going to print what I is, and it's going to calculate x from this operation, and it's going to give me this output. So we expect 3 lines of output here, one for each iteration. And lo and behold, we've got the first element, 12, 22, and 34. And each time we've got the result. Kind of important and possibly confusing for beginners is that the I here is totally arbitrary. Really what it just stands for is we just want an element in this list. So I could write element, I could write hullabaloo, or I could write whatever I want. The point is just to be consistent, that's the character, that's a variable that you're going to want to use. So just to demonstrate this point, I've substituted I with whatever. Notice whatever is also not a variable that I previously defined. And the code is just going to run all the same. There is no difference. Notice also that the x is kind of arbitrary as well, and it was a variable that was previously not defined either. But at the end of this for statement or for loop, what we've got is that x, x was first defined as the multiplication of the element by 57. So first it ended up being 684, but by the last iteration it's 1938. So now x has been kept as that variable. I'm gonna skip over this sort of more elegant formulation and go on towards talking about libraries and modules. One of the huge advantages of using Python is that there are amazing libraries out there. Some of them are inbuilt, and others are created by a really, really large and always active sort of free community of Python users. And for you to understand what these libraries or modules really are, I want to start by talking a little bit about this idea of namespace. So namespace is basically the set that contains all the variables and objects that we have defined. Well, that's not actually 100% accurate, but because it also contains sort of inbuilt variables. But let's just talk about the variables and objects that we have defined for the moment. So the current namespace contains things like my string and my list because we defined those. But now a sort of question to you. Have we created any variables called x or y? Let's see how Python relates to these things. So I'm going to ask Python to print my variables, my string, my list, x, and y. And we get an error message. Predictable, but the error message is not the only thing we get. First, Python evaluates the first line and says, yeah, I can do that. My string, I know what that is. This is a string that I just wrote and then added some text to. Great. Python then looks at, print my list. Yeah, I can do that. We've got this list, my list. So Python gives me that as an output. And then finally, or not finally, it looks at print x and says, yes, we defined x in that for loop. It was the last iteration defined x as 1938. And then Python looks at print y and is like, I don't remember any y. And helpfully tells us there's an error here. In fact, it's a name error. It's in line 4 of this cell. And the error is that the y has not been defined. So x is in our namespace, but y is not. So if I define y, say, give it the answer to all the questions in the universe, 42, then if I rerun the above code, it's going to work just fine. And now Python understands that y is 42. But now let's remove everything I've just defined. I'm going to remove that from the namespace, which is a kind of radical move. So Python asks me whether I really want to do this, and I do. Now when I try to run just the same code, Python breaks down already at the beginning, obviously, because it doesn't even get to the rest of the code. It just complains that it doesn't know what my string is. So that's just to sort of show you that namespaces are populated by variables that we create, but not just by those. They're also populated by objects that exist in general, and functions and methods and so on. For example, and this is a bit of a tricky part of this talk, we might presume that something like a common mathematical object such as pi would exist, would be an inbuilt object in Python and would exist in a namespace per default. But it doesn't. So, and this is where modules come in. I'm going to skip over the part where I assign a random number to pi. What libraries or modules do is that they basically bring in new or not per default existing objects, object types, methods, functions, and so on to the namespace. So that's why we have to, every single time we want to use an object or a method type from a particular namespace, we have to import it, or from a particular library, we have to import it. So one way to get access at this pi object, which we would presume to be something like 3.14, whatever pi actually is to import the math module, which contains pi. So I'm going to do that. In this line, I basically import the math module. And here, what I'm basically saying is, from this module, I want to look at this object, pi. And what happens? Well, what we see is that the module has been imported, and now pi is assigned to a number that we familiarly know as pi. Great. We can also import, there's a bunch of different objects. William mentioned NumPy, and I'll talk about NumPy a little bit later. But here I'm just as an example, I'm going to import the time module. And I'm going to, from the time module, I'm going to call this method local time. So that's what happens in these 2 lines of code. And you see that the output is that I get this sort of weird thing that's a little bit hard to interpret. And it's kind of unwieldy, but basically what it tells us is what the current time is, at least for me, which I think might be a little bit different for those of you who are in Chicago. But that's kind of hard to say because this object is a little bit unwieldy. So what I'm going to do is I'm going to create a variable called t. And I'm just going to call this object again. So I'm going to get the local time for myself again, and sort of look at what type is this object. And we see that an object type called struct time in the time module is the type of this object. So this is an object type we didn't really have in our namespace before, but now it's there because we imported the time module. So we can use a method that was also imported in the time module, the which I think of as structure of time, we can use this method to convert this annoying looking object into something that we can read easier. So I'm going to call a new variable current time. I'm going to define it as basically taking this t variable, which I defined above, and using the structure of time method, I'm going to convert that variable t to a format that is specified here. This is a little bit technical, but don't worry about it. That's just the technicalities of this method. And then I'm going to print current time. And now we see that this is kind of useful for me in my talk. I know that I'm 40 minutes in. Oh gosh. That it's, for me, it's 11:40, and we can actually read that. What we can also do is we can import from math. So for example, from one module, we can also just import a single object. I'm not going to do that now, but that's another possibility. So you don't necessarily have to import the whole module as such. So what this means is that you're likely going to be needing to install some packages, because some libraries, modules, packages, or whatever you want to call them, are built in, but others are not. So you have to sort of install them. And there are two basic ways of doing that. One is you can use the terminal or the shell in Windows. For example, if you want to install NumPy as an example, and matplotlib, which are two packages, then you could use this code to do that. Another option would be, and I'm just going to quickly do a new share for just one moment to show you how you can install packages in Anaconda Navigator. So you might remember the Anaconda Navigator from the beginning of this talk. Well, you can go to the environments here on the left, and here you see that a lot of packages are listed here as installed. So I want to sort of search the not installed or all packages. I can search for NumPy. You can see that NumPy is installed for me already, so that's not very interesting. But if I look at the uninstalled packages, and I wanted to install GlueViz for some reason, then I can just click checkbox and click apply here. Okay, let's go back to our Jupyter Notebook. I'm going to skip the part about NumPy right now. Just basically mention that it's a Python module that's really good for working with numeric computation. So basically arrays, and that's more or less all you have to know about that for now. But I want to talk a little bit about pandas, which is another module that's very useful for data analysis and data science in general. So I'm going to quickly import pandas as PD. That's just, I can choose to do that. This means that I'm going to be using PD to refer to the pandas module. So you see here, PD rather than pandas. And the basic unit, the type of object that I'm interested in pandas is the data frame. So I'm going to create a table here, calling it table, that's going to be from pandas, a data frame. And I'm going to create two columns in it, which I'm going to call name and age. And then row-wise, I go through and assign those with information. So I basically supply each row of the data frame with information. When I do that, I can take a look at my table, and you see that this is what that data frame looks like. Sorry, I decided to go with all J's on the names. I don't know. I had just had a day. So suppose we forgot to add another column which specifies people's favorite novel. So I'm going to do that. I'm going to do that by adding basically saying, in my table, I want a new column. And this column, I'm specifying that as a list that contains elements. And these elements are all strings. And it ends with, you see, square brackets, so it's a list. So basically, I'm just using a list to sort of define a new column. And when I do that and I look at my table now, you see that a new column has been added. going to skip forward a little bit. And I'm just going to say that one thing that we can do is we can basically take our keys and our values from a dictionary to create a data frame. But for that, we need to use lists. So what I'm going to do is I'm going to, remember this was our dictionary, redefining it again, because I've cleared my namespace a couple of times, not really sure that it's still defined. And what I'm going to do is I'm going to take use the keys method on my dictionary object. Remember, we encountered this method before. And then I'm just going to use this function list to convert that object type into a list. So this new variable keys list is just going to be a list containing the keys, and analogously for the values. So you'll see that I'm going to check their types at the end here. So when I run this full cell, basically the only thing that we see as output is I've asked Python to print the types of these objects. But now I can basically create a new data frame, and I'm going to call it df. Again, it's a pandas data frame. This line is basically just setting up an empty data frame. So it basically tells me I now have a new object that's a pandas data frame. And I'm going to say, I want one column that's going to be called English. And I'm populating it with this list. Remember, this is a list object that we just created. And likewise, I'm going to create a column called French with the values list. This is exactly analogous to what we just did with adding the favorite novels. So I'm going to run that and then take a look at the data frame. And we've got what we wanted. So here, in just one line, I'm going to add German as well, analogously to what we just did. And we have that now as well. And just one short comment, that we can access a column, for example, by just calling that, just specifying that this is the column that I want from that data frame. Okay, skipping forward. So now I want to basically give you just a very, very short, brief intro into working with texts and counting word tokens. We're going to put some of what we've worked through together in order to do a very, very, very basic thing. And basically what we're going to do is we're just going to import text using a text file, save it to a string, do a little bit of text cleaning, although it's going to be a little faulty. And then we're going to count some word tokens. And we're going to run into an interesting basic feature of working with texts computationally. So what I'm going to do is in the folder or so if you set up your folder and you basically downloaded all the files that were sent to you, then it makes sense to put those text files that are in there into that folder as well. That way, when I define this file, I'm going to call it, or this variable, I'm going to call it input file. This should be the path where Python is going to be looking for that text file. Because in my case, all of these files are in the same folder, it means that that's where Python starts looking. So I haven't really had to specify much of a path. So that's why I recommend that you just save all the files into that folder. So I'm calling this variable input file, and it's a string that specifies the file path. Then I'm creating a new variable, which what it's going to do is it's using the open function. It's going to read in this file path. This is part of the function that specifies that I want to read it. And this is just an additional parameter that says this is the sort of character encoding. And then in this line, I'm going to redefine text as what we just got from the previous line, but I'm going to read it into a string. So when I do that, I'm going to take a look at this text variable. We get this really, really rather long string that starts with, Project Gutenberg ebook of Dubliners, blah, 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 blah. That's just because I just took this from Project Gutenberg. And it's one really, really long string. And we can easily say that wow, there's a lot of these weird like /n characters in there, and there's a lot of mess in here. So what we want to do is we want to clean it at least a little bit. So I'm going to use the replace method for that. Basically, what this method does is the first string specifies what I want to replace. And in the second string, I specify what I want to replace it with. Because I gave nothing, what this method will do is it will basically replace this weird string with nothing. In other words, it will clear it. And what I'm doing this to is, like with the syntax of methods before, I'm applying this to this object text. And once that is done, I'm going to do that again. And in the result of that, I'm going to clear this other character as well, which I don't think we're seeing in the output here, but which often frequently appears in strings that come in from text files like that. Great, so I run that and take a look at text again. Now we see that those /n characters are gone. And that's great. I'm gonna skip over some of this basic navigating string texts. Instead, I'm gonna move on to do some more cleaning and say, what we want is we want to make the entire text lowercase, analogously to the upper method that we used above, because we don't want to make a difference between, for example, if something, for example, this word every, if it occurs at the beginning of a sentence, it's still the same word as if it occurs mid-sentence. And the same thing applies for stuff that occurs right before punctuation. It's still the same true, whether it's mid-sentence or at the end of the sentence. So what I want to do is first, I'm going to convert everything to lowercase. But then I also want to specify the punctuation types that I want Python to clear out of this. I'm going to use the replace method for that. So what I'm going to do is I'm going to take the for loop, basically the same for loop structure that we looked at above. And I'm going to say that I've defined this list called skips for punctuation, for element, for whatever in skips. Basically, I'm going to take the text object, use the replace method, and replace that particular element with nothing. And when we run this cell, we're going to see all lowercase text with the punctuation gone. And that's what we've got. So notice that one of the things that I did not remove is I didn't remove the Project Gutenberg, blah, 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 that beginning. I haven't removed asterisks because I didn't specify that. I haven't removed hashtag. And also, it seems that there was something that went wrong with the character recognition here. So I would need to go back to sort of look at what did I specify wrongly so as not to remove those quotes. But I'm just going to ignore that for now because I don't have time. And instead, what I want to do is I'm going to take this whole text file. It's a string, remember? And I'm going to split it up into a list of strings that are individual words. And what I can say is I can differentiate these words because I see that they have spaces between them. So I'm going to define a new variable. And I'm going to call it split text. And you're going to use the split method and specify that this thing, space, is what I want to split my string around. So basically, when I do that, I'm going to get a list that has now separated that one long string into a list of strings, and they are all the individual words. And we can see that there are some errors again, because it looks like there was no space between Joyce and this, but I'm gonna just ignore that. And in the last 3 minutes, I'm gonna quickly basically count each word as it appears as an individual token, meaning, you know, we're looking at the word every before. I just want to see how many times every, the, whatever, truth, and so on appear in this text. So I'm setting up an empty dictionary, which I'm going to call word counts. And basically, I'm just going to use both a for statement and an if statement. The for statement is basically going to ask of Python to go through our list of words. So for each word in this list of words, split text, I'm going to ask, is this word already in the dictionary? If it is, in other words, if we've already counted it, then what I want to do is I want to increase its value by 1. Because in this dictionary, basically, I'm just going to have keys, which are going to be all the different words, and the values are going to be the number of occurrences. So if the word is already in this dictionary, then now that I'm encountering it again, this means that its occurrence, that its number of occurrences should be increased by 1. If not, in other words, if Python has not yet seen this word in our list of words, then I should just initialize a new key for that word and set its value to 1, meaning now I've added it to the dictionary. So when I run this, and then I'm going to take a look at my word counts dictionary, then basically what I get is what I expected to get, which is a list of all the individual occurrences, the individual types of words that occurs. And remember, the errors are still in here, so we still got Joyce this. And we get their numbers of occurrences. Skipping forward a little bit, there's an inbuilt way to do this, but not going to look at that. Instead, I'm going to ask, what are the 25 most frequent words? And those of you who work with text will know already basically what those will be. But what I want to do is I'm going to turn the keys of this dictionary, word counts, into a list, just like we did above. And the same thing for values, because remember that lists are ordered objects, but dictionaries are not. And this is going to be important just in a second. So I'm going to take keys and values using the keys and values methods, convert them to lists, define those variables. Then I want to sort those lists in reverse order, meaning I want to take the highest number of occurrence first, and then sort of sort in descending order there. I'm going to use the sorted function. I'm going to take a look at the values because those are the numbers of occurrences. Sort in reverse order, so descending. And then that's going to be a list where I'm only interested in the first 25 highest numbers. I'm going to take a look at those. So these are the highest numbers of occurrences of individual words in Dubliners. And now I want to find out, but what are the words that are associated with them? And we can use the index method to find that out. So basically, I'm interested, what's the highest number of occurrence? What's the order in the original values list? Where in values list does this number 3518 appear? What is its index? I'm gonna find that. And now I ran into an interesting problem. I'm sorry. Yeah, that's because I was using different. Yeah, so sorry, my apologies. So I'm interested in the highest number of occurrences. And it wasn't the number that I had. It wasn't 3518, but it was 3527. My apologies. So it tells us that the index in the values list is 0. And that means that it's going to be the first element, which isn't a surprise because I think we already saw it up here, but just for the sake of argument, what is the key that corresponds to this value, i.e., which is the word that has 3527 occurrences? So I'm just going to take that index and give it to our list of keys. And lo and behold, it tells us the. So now we know that the is the most frequent word. And we're just going to repeat this kind of convoluted exercise with 25 times. So we want to sort of see all of this for the top 25 most frequent words.
Daniela,
Yeah.
I'm sorry to cut you off. We need to wrap up. It's 11.
Okay, so I'm just going to run this and then I'm going to stop. And so we've got these. That's it. You can take a look at the rest of the document. It basically just does the same thing for Kane and in our time. I wasn't expecting to get to those. But the point is, and maybe I'm just going to scroll down to the end, is that basically what we've derived here is that the most basic words, the most frequent words in all of these three texts are going to be so-called stop words. And these are words that aren't necessarily particularly interesting for digital humanists, but a lot of our data with working with text is going to come from stop words, which are pronouns, prepositions, and so on. I've got a bit of takeaways here, some resources, including, I also included William's YouTube tutorial series. I thought that was a good resource. Thanks so much. And really, my hope with this was to be able to give you a little bit of sort of basic insight into how to use Python. And I hope that the logic of that was sort of clear. I know it was a lot, it was a little rushed, so I'm hoping you can hang in there.
No, it was great. Thanks so much. Let's see. We have some questions. We have one question. Let's answer this one question very quickly, and then we're going to take 5 and then move on to our last presentation. But A. Britton asks how to familiarize oneself with Python libraries. There are so many, and it feels overwhelming.
Well, that's a good question. So basically, my recommendation would be to start playing around with Python and sort of just see what are the applications that you're interested in. And so, for example, if you want to use arrays for some reason, you have no clue that which Python library is the best for handling arrays, then you basically just Google that. Or you go through and you will very quickly find that recommendations will come up saying, NumPy is the Python library that you're going to be using. So it's really just basically Google the application that you're interested in. So for example, machine learning also, William was talking about, scikit-learn would be a good module for that. And it's a lot of it is like, using a kind of computer logic, trial and error, and then just finding what you need.
Okay, great. Okay, we're going to take 5 minutes before the next presentation, which is Advanced Features of Scalar by our very own Janet Swachino. If you have questions for Daniela or also William, because he's still here, please put them in the Q&A and they will answer them during the break. If that works for you, Daniela and William, that still works for you, that would be great. Okay, cool. Okay, so everybody, we'll be back in 5. Okay, 5 minutes goes by so quickly, doesn't it?
Yeah.
Okay, we're back. Last, but certainly not least, is Advanced Features of Scalar by Janet Swachino. Janet is the digital publishing librarian at the University of Illinois at Chicago Library, and she's also the other co-director of the DHI. Before joining UIC, she was the digital publishing specialist at the University of Illinois at Urbana-Champaign and a Library of Congress Junior Fellow at the John W. Cluffe Center. And welcome, Janet. Thank you for being here, for presenting.
I'm going to share my screen. Here we go. Okay, so Scalar, what I'm going to be talking about today is a publishing platform called Scalar. And I wouldn't exactly say that it's an advanced tool for digital humanities. Instead, I'm going to show some of the advanced features in Scalar. And I say that it's not an advanced tool because it's actually quite easy for most people to just pick up, even if you don't have experience making websites and you haven't, used HTML or anything like that. It's fairly easy for anyone, including students, to just kind of pick up and start using. So what is Scalar? It's a free open source authoring and publishing platform that's designed to make it scholarship online. So it was created by this Alliance for Network Visual Culture, ANVC, from the University of Southern California. And it has a pretty flexible it's a pretty flexible platform, and it allows authors to impose structure on their work. So unlike a traditional website where you might see menus and you kind of click around using those menus, Scalar really lets the author decide how they want their readers to navigate through the content of their work. And we'll take a look at some examples. The other thing that it does is it allows authors to assemble media from multiple sources and juxtapose it with writing. It's very good for essay and book length works that you want to, things like videos and sound. So let's look at some examples here, and I've already pulled them up. So here's one called Digitizing Sleep Cultures by Hannah Huber, who I believe is in the audience. So she can always say something in the Q&A if she disagrees with what I'm saying about her book. So this is, she created this, if you are a faculty, student, or staff at UIC, you have access to Scalar through Digital UIC. And so you'll see right from the beginning, it kind of doesn't look like a standard website because it's telling you to begin on a certain page, right? It doesn't really encourage you to kind of click around. Now there is a menu up here on the right that takes you to the table of contents, but really like the main part of the page is kind of telling you to go to this, begin with the About section. And while that's loading, I'll see if there's some questions here. Okay, when we are done with this part of the workshop, could you point us to additional opportunities for Scalar training? Yes, so that was from an anonymous attendee. I can point to some, there are a lot of good online tutorials that exist for Scalar, and they have really robust documentation, which I have linked to in the PowerPoint, which will be shared as well. Okay, so so like I said, the very first thing it does is it tells you her information, and then at the bottom, and you'll see this is a common thing in all Scalar books, it wants you to continue to the introduction. So it's going to lead you through the material in specific ways. And I'm not going to get too in depth into like one particular example, but I wanted to show you there's a lot out there. So there's this is called Victorian Ghosts, 1852 to 1907. This is it with students. So in this particular example, he's assigned students Victorian ghost stories. So all of these things are in the public domain. And then I'll go to one right now so you can see. So the students have the text from this public domain ghost story, and they are annotating using notes here, different parts of that story. And then they've also created essays around each of the stories. So that's available here under this essay section. So again, it kind of takes you through each Victorian ghost story. There are annotations, and it's structured the way this particular author wants things to be structured. Okay, and then the last one I want to show is this is one published by a group called Raven Space, and Raven Space is a number of different universities working together to publish Indigenous stories, and what I really like about this is they've highly customized Scalar. So you can, if you know code, if you know JavaScript, if you know, if you want to get deep into customization, you can. And so what they've done is customize this so it prompts the reader to accept a cultural protocol before reading the book. Let's see if it will pop up here. I think maybe because I've gone to this a few times, it's remembering me. Okay, while that loads, I'll look at the Q&A again. Okay, so someone is asking, is Scalar a self-publishing tool? Do you need certain credentials to access the platform apart from setting up an account? So it is a self-publishing tool. You can access it directly from the University of Southern California, or if you're at UIC, you can access it through digital.uic.edu. Okay, so this is what I was talking about here. They've customized their version of Scalar to prompt you to read this protocol for being a special guest, a respectful guest. So you kind of have to agree to read the book in the way that they're asking you to, right? And not share things you're not supposed to share, etc. So before you can enter, you have to say "come ashore." And if we go here, you'll see they've made a number of like really it's highly customized. They've made some decisions around what the pages will look like and how people will navigate the content, which is a little bit different than what you get out of the box. Okay, let me go back here. So for getting started, and again, I'll share this PowerPoint so you have access to these. UIC has a research guide on Scalar that's very kind of bare bones, just how to start, how to create a book and create a page. So really the most basic things you need to know how to do. The Scalar 2 users guide is what I would recommend looking at, and that's USC created that, is in there. And then anyone can sign up for a free account through here. I'll put this in the chat. And then anyone at UIC, you could also get one through digital.uic.edu. The difference there is you'd have a UIC domain, right? If you use the Scalar version, your domain is going to be scalar.usc.edu. And then they do require you get a code in order to, you have to fill out a form to get code. Just be aware that can take some time, but it's to avoid them getting. Okay, so what I'd like to do today is do like a tour of the back end and then show you how to import an annotated piece of media and then reference that annotated media on a piece of media. And then import visualizations from outside websites, and then use Scalar's built-in visualizations to visualize some of our tags. And then if we have time, I can talk about the editorial workflow. But since I don't want to keep people over, I might just kind of run through that quickly because it's not going to be relevant to everybody. Okay, so some important concepts to keep in mind. Media is a huge part of Scalar. It's one of the best parts of it is you can import it easily. You can embed from outside sources. So I'll show you how to do that. And then tags, tags. Pages can be tags, media can be tags, pages can tag other pages, media can tag pages. It's a really powerful thing if you take advantage of it, but not all Scalar books take advantage of it. You don't have to use tags. It just can be a good way to connect and that they relate to each other. And then lastly, I'd say plan out your work ahead of time, but explore and play around. So I have, what I'll be showing you and working in is my practice book, where if I have an idea, I just go in there and create a page and try it out. But it can be very overwhelming. So if you're thinking of doing some long form scholarship in Scalar, or you want to work with the class to create a Scalar site, I would definitely recommend planning it out ahead of time and creating that structure before you dive in. Otherwise, it will be harder in the future to connect it all. Okay. So I'm gonna go. So this is my practice book that I've had from The Devil's Dictionary by Ambrose Bierce, which is a text that is also in the public domain. And I've created just a few pages of this writing. So The Devil's Dictionary, it's looks like a dictionary, but each of the definitions are satirical. So like here, one of my favorites is down here. Academe, an ancient school where morality and philosophy were taught. Academy, a modern school where football is taught. So just kind of funny dictionary definitions. And then he goes throughout and has all these fake quotes, which I also find lovely. And so I use this to kind of show how you can create annotations and you connect pieces of media with different parts of the text. So this is what a page looks like in Scalar. But what I want to show you is what the dashboard looks like. So if I go up here to this little wrench, that's going to take me to the back end of my site. And the very first thing I see is the book properties. So the title of my book. Here's the table of contents. So as you create pages and you want to get that table of contents over here, that's where you add it, is on this page. This is also the page where but if you need to create a new book, you would go to my account and then just create a new book here. So you have to enter your title and then click create. And it also shows you any other books that you're a part of. So again, I'm already in my practice book here. And if I go to book users, I can see who else is here. Right now, I'm the only one. And I'm an author, but you can add other types of roles. So not everybody has to be creating content. They can be an editor, they can be a reader. And then sharing here, this is where you would go once you're actually finished with a project and you want to make it public. You would change this availability to make the URL public, yes. So just be aware, it's private until you've decided you don't want it to be private anymore. Okay, so there's these two tabs here. These are where you'll be working the most. So pages allows you to create new pages, right? So that's how I created that A page we were looking at. And then you can see all the other pages that I have. Not all of them. If it's kind of red like this, that means it's not an active page, like you can't actually see it anymore. So I deactivated that page. Where we will start is this media tab. So media is when you want to bring in media from outside sources. And I have already picked out a piece of media here. Okay, so this is the, it's a phone call from Trump to the Georgia secretary to asking him to recount the election votes, right? And I found it on SoundCloud. The reason I picked SoundCloud was if I go over here to this import pages section where this is where you'll import your media, Scalar has some affiliated archives that they already have a connection to, so they can bring in information and it will save you a lot of time, basically. You won't have to enter metadata about that item. So I purposely wanted to find something that was on SoundCloud. You can, so if I click here on the SoundCloud, you can browse SoundCloud directly from here. I don't find that it's like the best interface for actually browsing SoundCloud. Like if you go to SoundCloud itself, they have a better browsing experience. So that is how I found this particular clip. And so now what I want to do is I'm just going to take the title and search for that directly. And it comes up. So that was easy because I had the full title. Again, you can try. I could have searched for Georgia secretary. I could have searched for Trump phone call, and something would have come up. But I just find that searching on the affiliated archives own site is a little bit easier. So then I'm going to click this little button. You can preview it here if you need to preview before you import it. And then you'll just do import selected. And then see, this is what I was talking about, having it kind of bring in all this information that saves you a lot of time. So they already have a description of the video. They have a link to the original recording. So you won't have to enter that information. Okay, and then there was a question in the Q&A. Okay, so one of the, let's see here. Is it possible to associate our own digital collections archives with our Scalar instance? From Anna Hanlon. Yes, it is possible. So Scalar has an API. So you can, you would have to get your own instance of Scalar. So you can't use the USC version of Scalar unless they want you to become an affiliated archive. You would get your own instance of Scalar, and then you would use that API to connect with your own digital collection. So yes, it is possible. And then there's another question here. How much do you create the sites in your job, and how much do you show other people how to create the sites on their own? So in my job, I just show people how to create sites on their own. I'm not very hands-on with creating the sites for people. Okay, so so it's saying a file has been imported, and I can follow the link here to see it. So now it has this this full phone call. It's really nice because, especially for large audio files that you don't want to like host yourself, if it can be hosted someplace else and you just reference it, that's great. And that's what's happening here. Now, one of the things that could potentially happen is if Mystic Horse, I don't know who Mystic Horse is, if Mystic Horse decides to take down this call, then it's not going to work anymore on my site, right? Because it's referencing an outside site. So that's just something to keep in mind. It does, you know, it makes it really easy to use media, but then you have to be aware that that media could go away when you don't control the media itself. So from here, I now have his phone call, and I can go up here at the top, and this little clip icon here is the annotate button. So if I click the annotate button, it takes me to an annotation editor. And what that allows you to do is play the clip, and I'll play it here, but I don't know if you'll actually be able to hear it, because I don't know if I'm sharing my computer audio. So you can play the audio, and then as you play the audio and you find a piece that you want to, a portion of it that you want to actually annotate. So let's say at the 1:49 mark here, I want to add an annotation. You would just click this add button, and it knows where I am. It knows that I'm at the 1:49. And I can give that annotation a title. So maybe this is the point where the president asks for 11,000, what was it, like 11,800 votes. So maybe that's what I title it, or I just title it 11,800 votes. And then I give a description here. And then I would just click save. And of course you can set these to be exactly where you want them to be, both the beginning and the end. And what will happen is when someone plays the media, those annotations will pop up. Okay. Let me just see if there are any other questions. Okay, I don't see questions, but so you can just continue to add annotations as you go through the audio. And this also works for video as well. So you can import video, play the video, and then add annotations as you listen to that or watch that piece of media. So let's say I'll just add one more here, maybe at the 4-minute mark. I haven't actually listened to this whole call, so I don't know what they talk about at the 4-minute mark. But let's say they talk about Georgia ballots right now. Okay, so now that I've imported my media, I've added some annotations. Let's say I want to go back into my text here and actually add this piece of media to part of that text. So I'm going to go to my B section here and find something that I want to comment on. Oh, see here, I already have. I've already done this in the past, added it to beg here. So I'll show you how I did that. I went to up here at the top, you have all these little icons, and the pencil icon is for editing the page. So I'm gonna click this edit button, and it shows me all of my text in a WYSIWYG, a what you see is what you get editor. So you can do things like make things bold, which is what I've done here. You can put things in quotes. So definitely explore all of these little options up here for your text. And then I went to the word that I wanted to comment on, and it was this word beg. I'm going to just remove that for now and add it back in. So in Scalar over here, you have these different ways, these blue buttons here are different ways to add media to your page. And if you kind of hover over it, it will tell you what it's going to do. So we'll either insert a Scalar media link, insert an inline Scalar media link, which is like, it won't be attached to a word, it's just on your page. Insert a note. So we looked at those students' work where they had created notes for each, for different words in the Victorian ghost stories. That's how you would add notes. And then over here, this insert Scalar widget link, that's another thing we'll look at when I talk about visualizations. That's for creating, that's for inserting different Scalar widgets. One of those widgets is a visualization widget. So I just, what I'm going to do is highlight the text that I want to be connected to that piece of media. And I'm going to select, and I always get these mixed up, but I think it's insert scalar media link. And what that does is it brings up all of the media that I've imported. So in this case, I want this full Trump pressures Georgia Secretary of State to recount election votes. I think that's the one I want. Yes. Go back up. So I'll just click on that. Oops, oh, it took me back out to what I actually want is to not click on the link, but click there. Okay, and then it will let me decide how I want it to be formatted on the page. And this is something you really have to, like try it a few times to see what you like the best. So not everything looks, you just have to kind of play around with the settings to get it right. So like when I was playing around with it earlier, the small was way too small on the page. You couldn't really see the media there. So I'm going to pick medium and I'll have it align right. You could align it right or align it left. You could decide to have a caption. You don't need to have one if you don't want. I'll keep the description as a caption. And then down here, you'll see these annotations that I created. So when you just do it automatically, it's going to hide the annotations. If you want those to be visible, you would just unhide them here. So then if someone clicks on the audio file, those annotations will pop up as they're listening. So then I would press continue. And down at the bottom here, save and view. And then if I scroll down to beg, now this is associated with the media. And if I press play here, let's see if they'll pop up. Okay, at 150. Let me just try to find it. There we go. I don't know why it's not popping up, but okay, let me see. There's a question real quick. So from Dina Strong, I'm wondering if anyone's done an accessibility review of the various techniques for embedding media and connections here. Dina, that's a good question. I know that that ANVC does accessibility view like checks. I don't know how it's probably pretty impossible to check like every possible way you could embed media, but yeah, I mean, I think it would be a good idea to do that. My experience with Scalar and accessibility is that when they've made improvements, so like for example, they've changed how they do alternative now I can't think of the word, alternative text for images. So I know they do reviews. I don't know how they're doing it for embedding specific media. Okay, so let's see here. The other thing I wanted to show was how to add tags. So if I, again, go into this editing area, I'm going to scroll out here. Down at the bottom, you'll see a tab called relationships. And there's a lot of different types of relationships things can have in Scalar, like annotation, comment, path. That's like a whole nother thing in Scalar, is creating the paths. But if I want to tag this page, I would click this tag button, and it's going to give me two options here. I can, to make this page a tag, so I can tag a different page with this page, I would click here. But if I want to add a tag to the page, which is what I want to do, I want to tag this page with a piece of media, I would click this choose the items that tag it. So in this case, I'm going to tag it with not a page, but with a piece of media. And I'm going to tag it with this, the phone call that I just added. So now if I do save and view, down at the bottom, it will show me that this page is tagged by the phone call. And the reason I did that is because I want to, the next thing I want to show you is how to add visualizations, and including some of the built-in visualizations using the tags. Okay, so I want to just stop before I go to visualizations and ask if there's anything about annotations that if people want to ask in the chat. Okay, I don't see any. So I'm going to go then to visualizations. So visualizations, again, similar to media, you can bring them in from outside sources. If we look at one of the books that I worked on, where I was doing more of like actually making technical edits to the book, this is called the Jay-Z mixtape. So he has embedded, Kenton Ramsey, the author, has embedded visualizations from Tableau. So Tableau is pretty commonly used visualization software, and he's just used their embed. They have an embed code, and you can embed it on your web page, and that's what he did. For this demonstration, I'm going to use this this visualization made by Nicholas Lambert on COVID vaccinations. So this is from, he's using a website called Observable, and the type of visualization is a D3 visualization. You can see all of his code for it here, which is nice. I just want the visualization itself. So and this is going to be pretty much the same for any, if you create a visualization in Tableau, in Observable, in Flourish, whatever tool you're using, you'll want to look for the embed code. And in this case, really all I need is the link. So I'm going to click on these three dots here and embed cells. Observable, you can like really pick what exactly you want to embed. I just want the chart itself, but you could pick all of these things if you wanted. You could do the entire notebook if you wanted. And then I'm just going to take the URL. And then again, using the import pages, I'm going to import this visualization. So I'm going to go click on this wrench, will take me to the dashboard again. And then under media, and media or pages really will work, but I'm going to pick media. And then I'm going to pick import pages. And this time I'm going to select internet URL. So this is, I'm just referencing a URL. It's already out there on Observable's website. I can give it a title. And then I just need the URL here. And then I'll click Save and View. And now his visualization has been imported. But what I found people really, so so using visualizations from outside sources is great, but a lot of people are also interested in how to use the built-in visualizations available in Scalar. So the built-in visualizations are all related to like how your content is connected with other content in your book. So what I'll be showing is how to make a visualization of the tags in a book. So I already have started a page. So I'll go back to this little wrench here. And this time I'm going to go to my list of pages. And the one that I've started is called Visualize Tags. So I'll go to that page. And I don't have anything here yet because I haven't added the visualization. What I'll do is click this edit page and I'm going to be adding it. So previously, we talked about these little tools up here, these little blue buttons. And one of them that we mentioned was this, oops, I'm sorry, this one right here, adding a scalar widget. So there's lots of these different widgets. I recommend playing around with them. There's a mapping widget, a carousel widget. We're going to be using this visualization widget. So I will pick that. And then it's asking me a few questions. What kind of content do I want to include? So I could visualize all the content in my book. I could visualize just a table of contents. In this case, I want to visualize the tags. So things that I've tagged with other pages I've tagged with other pieces of media or other pages or just tags. And then what relationships would you like to visualize? I'm just going to pick all relationships. And then finally, what type of visualization would you like to use? There are these 4 different ones here. The tree is like, if you're trying to visualize, if your book is very hierarchical, you might use that tree visualization because it will show you how everything is connected as a hierarchy. What I like to use is this force-directed visualization. You'll see it shows how things are connected using, it's called a force-directed graph. And then again, I get to choose, do I want it to be medium, large? Do I want it to be aligned, in the center? Again, you have to play around with it and see what looks best on your page. And then you would click Insert Visualization. And down here at the bottom, I'm going to click Save and View. So this is showing me my pages are these yellow pieces here. So I have an A page, I have a page for the letter I have a B page, and then the red are my pieces of media. So A is tagged by all of these different pieces of media that I've uploaded over the years. And then same with, this is the one we just did. So here's my B page and the piece of media, and then the 2 here in the purple are my annotations. So it could be as you build out a long publication, especially when a piece of media is annotating multiple pages. Okay, so that's it for visualizations, and those are the main things I really wanted to talk about. I will quickly mention that a newer feature of Scalar is a built-in editorial workflow. So if that is something you're interested in and want to explore, I will include the information on how to, their documentation on that editorial workflow. But essentially what it allows you to do is, as the author, everything will be in a draft status. And if you want to make use of their editorial workflow, you can send it to editorial review. And this will make it, this is something that, especially different, like places like Ravenspace, some academic publishers asked for this functionality because they want to be able to have things peer reviewed in a way that's really easy for editors to read it all at once and peer reviewers to read it all at once, instead of having to like click page from page and then provide their feedback someplace else. So the editorial process allows editors and reviewers to give feedback directly in Scalar and not have to go to a different program to do that. But again, you know, if you're just going to be self-publishing, you maybe you're not as interested in that. It could be useful if you're going to have students work on a Scalar site together, though. So I'm going to end it there. Stop sharing.
Does anyone have any questions for Janet? My heater's on. Links for Scalar training. Can you share those in the chat if you have some? Perfect.
I will.
Okay, great. So I have one question. I feel like this is probably a pretty basic question, Janet, but as far as visualizations go, so it looks like Scalar's visualization widgets, there's only 4 different kinds of visualizations you can do. Is that right?
Yeah.
Is that, so how, is it better to use those, or is it better than to use Tableau and import? I'm assuming Tableau has a lot more options for visualizations, correct?
Yeah. And so Scalar doesn't really, it only allows you to visualize like your own book, basically. So if you have outside data, you would want to use something like Tableau or Flourish or Observable, which is the one that I imported, because Scalar is really only going to let you kind of visualize things that you've done in your book. So if you've used a lot of tags, it could be really useful. Or you've somehow, you know, you want to visualize your table of contents or your keywords or something like that, you can do that. But yeah, probably you'd want to use an outside visualization tool.
Yeah. Okay. Yeah, I'm familiar with Flourish, but I'm not very familiar with Scalar yet. So thanks, Janet. Does anyone have anything else? If not, I think we're gonna wrap up if that's okay with you, Janet.
Yeah.
Yeah. Okay, great. Well, everyone, this concludes our spring 2021 workshop. I feel like this was a great continuation to our fall workshop that we had in September. So perfect, great. Thanks to William. Thanks so much, William. And Daniela. Thanks so much to Daniela. She had to leave already, but and thanks to Janet so much. Deepest gratitude, all of you. And thanks to everyone who joined us today. We encourage you to check out our website at dhi.uic.edu for news and upcoming events. So like I mentioned earlier, we will have another half-day workshop-y type event. We do what we can here in virtual life on Zoom in early April. And I will post news about that on our website. If you have any questions or comments about today's event, you can find my contact information on the website. And that's it, everybody. Thank you so much. Oh, wait, do we have more questions? I see 4 now. Oh, just everyone saying thank you.
Just thank yous.
Thank you, Joe and Miguel.
There was more than one person who asked if it'd be recorded, and it is recorded. Where can people find it online?
Yes, so it will be uploaded to the event page on our DHI website before the next event. So around late March, it'll be uploaded. We try to sort of release the recordings close to the next event so that people can sort of see how they are connected, right? We try to make things logical here at UIC. Anyway, yeah, okay, I guess we're done for today. Everyone have a great Wednesday. Enjoy that weather down in Florida, William and Janet. I guess we'll be digging ourselves out of this 3 feet of snow for a while still. Okay, thanks everyone.